Welcome back to statistics. I got another nice probability distribution for you today, something called the Poisson distribution. Now, before we tackle this, think back to what we did last time. What was that called? That was called a binomial distribution. Can you remember what situation or situations, what kinds of situations the binomial distribution was good for? It was great if you were going to toss a coin a whole bunch of times or maybe roll dice a whole bunch of times. It applied to what we called Bernoulli trials. Bernoulli is the name of a person. Bernoulli trials, where you had a fixed number of trials. Remember, you're going to flip 100 coins or you're going to roll 48 dice or whatever it is. You had a fixed number of trials. The probability of what we called success, I'm trying to get heads, I'm trying to get a 6, whatever, constant on all of the trials. All trials are independent, right? No one trial depends on any other trial. That kind of stuff like that. Was there anything else? Oh, probably, but you get the idea. Flipping a whole bunch of coins, rolling a whole bunch of dice, or even you could say polling a whole bunch of voters where you could assume, well, it's kind of like the chance of somebody liking chocolate is supposed to be the same every time I ask a person. 20% of the population likes chocolate, then the probability any one person likes chocolate is 0.2. So it's kind of like a Bernoulli trial in that case. But anyway, the Poisson distribution. This is a new kind of process we're going to look at today. It's not altogether different, but you want to think in terms of like buses or meteors. Waiting for a bus, I should say. Or waiting for a meteor, right? It's like, yeah, you kind of expect a certain number per year or something, or maybe whatever, per time period. But theoretically, you could be waiting forever. I once waited forever for a bus. It never came. That was a bummer. Anyway, so what are the characteristics of a Poisson arrival process? Well, first of all, each arrival, each meteor hit, each bus to show up, whatever, each arrival is completely independent of all the others. This should ring a bell. I was just talking about that with the Bernoulli trials. Each coin flip was independent, or I should say the result of each coin flip was independent of all the other coin flips. So each arrival is completely independent of all the others. When does the next bus get here? Well, it's got nothing to do when the last bus got here. When's the next meteor showing up? It's got nothing to do with when the last meteor showed up. We're kind of assuming that, a cluster of meteors, we would probably count that as one hit. Anyway, you expect a certain number of arrivals in a time period. You do expect, like, I'm going to get hit with one meteor usually every month on average, something like that. Or 10 meteors every 1,000 years on average, whatever. You expect a certain number of arrivals or hits in a time period, some characteristic time period. And that number of hits in a certain time period, we call it mu, it's called mu. But other than that, it's completely random. So there is something you expect. It's not random. But with the exception that you have a certain number of arrivals that you expect, it's otherwise completely random. Now, you might expect 2 hits per year. That doesn't mean you're going to get 2 hits this year. It doesn't mean you're going to get 2 hits next year. It just means that over the long haul, on average, we would expect 2 hits per year. That's all we're going to say here. Otherwise, completely random. Nothing's guaranteed. And here's another one. There's no limit, and this is what makes it very different from the Bernoulli trials. There's no limit to how many might arrive in a particular period. So if you're rolling 100 dice, you're only going to get 100 sixes at the most, right? But if you're waiting for meteors for 100 years, you could get 18 jillion meteors in that one year, theoretically. Not likely, but theoretically. No limit to how many might arrive in that period. Think bugs on a windshield, right? So each arrival is completely independent, we assume. You expect a certain number of arrivals in a certain time period. That's called the mu. That's the thing that defines your particular Poisson distribution. No limit to how many show up. Okay. So the first thing you might notice here is we need to specify what time period we're interested in. Notice we first need to specify the time period we're interested in. Are we interested in how many meteors every year? Are we interested in how many meteors every 1,000 years? Are we interested in how many bugs every minute? How many bugs every hour? How many bugs every day? You know, we first need to specify the time period of interest or something. Yeah. Okay. So that's something it's going to be the first thing you have to do with every question. So let's start looking at some questions here. I got, I think, 3 kinds of question here for us today. So the first kind is, let's just talk about, well, what's the typical number of arrivals we would expect? So for example, the U.S., I looked this up, but I looked it up a few years ago, so it may have changed, but had 268 earthquakes in the past 41 years. Let's just go with that. 268 earthquakes in the past 48 years. So you might say that that's what we expect. We expect 268 earthquakes every 41 years. Okay. Is 41 years our period of interest? Well, let's look at part A. Expressed as a 95% probable range. How many earthquakes should we expect over 41 years? How do you like that? We are interested in a 41-year period. So mu, let's go back to blue. Mu, a blue mu, would be the number expected, and since they're asking us about over the next 41 years, it'd be the number expected in 41 years, and they flat out told us we expect 268 in 48 years. Cool. Now remember in the binomial distribution towards the end of the lecture, really, we did this 95% probable range thing. And back then, not that long ago, but we said you could take the mean, add or subtract 2 standard deviations, and that gives you a 95% probable range. I mean, approximately. It's not exact, but approximately a 95% probable range. Same thing here. Now for the binomial, remember mu was equal to n times p, and sigma was equal to the square root of npq. That was for the binomial. Okay, what do we got here? Well, the mu is what we just figured out. How many do we expect in our time period of interest? We expect 268 in these 48 years. You want to see a cool formula for sigma? Watch this. Square root of mu. That's it. That would be the standard deviation for a Poisson distribution. So continuing right along here, we can say, okay, so mu is equal to 41, and sigma is equal to the square root of 41, which I think I worked out, didn't I? Yeah, 16 point, whoops, not 41, sorry. Mu is the number of arrivals we expect in 41 years. It's 268, right? I mean, I said it right there. It's 268, and so sigma is the square root of 268. Okay, this feels better. And that comes out to about 16.37 or so. And so when we do the mu plus or minus 2 sigma, what we get is 268 minus 2 times 16.37, round back to 1 decimal place, I end up with 235.3 on the low side. 268 plus 2 times the square root of 268 is, I get 300.7 on the high side. And I like to do this. I'm going to start doing this. Since I'm talking about 95% chance, I'll put the little 95% next to that, meaning that roughly 95% of the time we'd expect to get between 235 and 301 or so earthquakes in 41 years. Cool. So you see how this Poisson arrival distribution works. It's just you figure out the mu, and sigma is an even easier formula, not square root of npq, just square root of mu. It's great. Next question, expressed as a 95% probable range, how many earthquakes should we expect each year? So notice we're changing the time period that we're interested in. Not 41 years, 1 year. So you start with the same given info here. They're saying expect 268 quakes every 41 years. But you can use a ratio and proportion here and say, well, how many do we expect in 1 year? Right? Because the period of interest is now 1 year. So I have to work out if it's 268 in 41 years, how many is it in 1 year? And a proportion is the easiest way to represent that. And you end up getting, what did I get? Where am I? What? Okay, I'm over here. 6.53659. just carrying a lot of decimals just to be funky. So we expect something like 6.5 earthquakes every year. Wow, they can't all be huge. They don't all make the news, I guess. But about 6.5 earthquakes per year. As a 95% probable range, we would want to do mu plus or minus 2 sigma. We would say sigma is the square root of mu, which, did I work out that number? I don't think I did. So what is that? Square root of 6.53659, boom! 2.56. No sense carrying so many decimal places, really. So when I do the mu plus or minus 2 sigma, I ended up getting about 1.4 on the low side. I like rounding off to 1 with these things. To about 11.6 on the high side. And I'm going to, again, write this 95% in parentheses to kind of specify where these numbers come from. What are these numbers telling me? Well, they're telling me that 95% of the time we'll get about 1.4 to 11.6. And I guess we could write here, just to be really official, earthquakes in any given year. Anywhere from like 1 to a dozen. Boy, that's quite a range. Quite a range, but dems to facts. So, and by the way, there's examples of people sort of verifying these things. Like, I saw this study once where they were talking about V1 rockets landing on London during World War II, and it really did make a pretty good Poisson arrival process. It was kind of interesting that it worked, but anyway. Let's do one more here on this page. This one I just kind of was interested in. Just curious what happens here. So the number is debated. In other words, I Googled it. That's what that means. I Googled it, and it says the U.S. economy has experienced 48 recessions over 240 years, going back to the Articles of Confederation. 48 recessions in 240 years. So let's assume a Poisson random arrival process. So how many recessions should any one president get, or to be more specific, in any one presidential term, which is 4 years? So the period of interest is one presidential term, 4 years. Okay, so let's figure out what the mu is. They're telling us we should expect 48 every 240 years. So the question is, how many would we expect in 4 years? Set up a nice proportion, bang it out. It comes out to a perfect 0.8. We expect about 0.8 recessions per president. Boy, that's not good odds, is it? It's like, hey, I'm president. Oh man, there's going to be a recession. They're going to blame it on me because it happened when I was here. What am I going to do? Anyway, let's look at the range here. What's the typical range? Well, sigma would be the square root of mu, which means the square root of 0.8. And that comes out to, well, it comes out to 0.89 actually. So then if you do the old mu plus or minus 2 sigma trick and round off maybe a little, maybe not, you get from negative 0.98 to 2.58. Now, a negative number of recessions is completely meaningless. We want our results to be meaningful, so we'll say anywhere from 0 to like 2.6. And again, that's a 95% certainty, or whatever you want to call it. 95% of the time, in a presidential term, we could get hit with anywhere from 0 to 2.5 recessions. Boy, you'd hate to get hit with 2.5 recessions in your one presidential term. No way you're getting elected. No way. But if we model it as a random arrival process, that stems to facts. And you know, the stock market is kind of random, so who knows. Okay, so that was those are all one of the 3 kinds of examples I wanted to do. The old what's the typical range question. Now we're going to calculate some specific probabilities. Like, here's the special case. This one's the easiest. What's the probability that you don't get any arrivals in your period of interest? So there's a formula for that, actually. So maybe I'll put it in a different color here. The probability of exactly 0 arrivals is, you ready for a nice formula? E, that's that number 2.71828 approximately. There should be an E button somewhere on your calculator. You might have to look above the LN button. Like if you have to shift LN, you can get your E or whatever. Anyway, it's E raised to the power of negative mu. Now, isn't that an elegant little formula? E to the minus mu tells you the probability of exactly 0 arrivals in your time period. So here's a Here's a darn practical example. According to Google, big meteors, 35 big meteors. And by big, I'm talking about that Siberia 1917. You heard of that one? I think it's Tunguska. I think I've got the right word. Anyway, big meteor, boom. About 35 of those hit the Earth every 1,000 years. That's what Google says. 35 every 1,000 years. Wow. So if we wait another 1,000 years, we should get like a lot of those. Okay, cool. 35 of them. That's nothing to sneeze at. So here's a question. Just focusing on the next 50 years, what's the probability we don't get hit? Because that's what I'd like, is to not get hit. What's the probability we do not get hit in the next 50 years? Well, our time period of interest is 50 years. So we got to figure out how many do we expect in 50 years. So take the given information. There's 35 hits every 1,000 years. So the question is, how many hits is that every 50 years? And if you work that out, it comes out to, what's it come out to? Where am I? What? There it is. 1.75. Wow. We expect 1 3/4 big meteor hits in the next 50 years. How about that? I don't like that. But anyway, the probability that we don't get hit at all, following the formula up here, is you take E, 2.71828, raise it to the negative 1.75 power, and that's all you got to do. And that comes out to 0.173774. So if I were to, I like to put all 6 decibels down, throw them all down, and then I kind of look at it with an artist's eye and say, where would you round that as a percent? I would call that 17.4%. Maybe I should put a little, approximately equal to 17.4%. Boy, that's not so good. That's a little better than 1 in 6, but wow, something's going to happen, folks. Watch out. Watch out. Okay. Part B, what's the probability to get hit at least once in the next 50 years? Okay, we've seen this kind of a question come up a few times. Are you remembering? Is this triggering something? Is your Pavlov dog drool response kicking in yet? Remember, at least once. Is the complement of nunts. Suppose I should use real words, right? The complement of not at all, or none, I guess, or no hits at all. No hits at all would be nice. If it's not the situation that there's no hits at all, well, you must have got hit at least once, maybe multiple times, right? So it's basically 1 minus, and that's the probability of no hits. And I'll use the rounded result, I suppose. So just about 81.6%. No, I'm sorry, I can't subtract. 82.6%. There we go. So it's about an 82% chance we'll get hit at least once in the next 50 years by a Tunguska-size meteor. Somewhere on Earth, who knows where. Maybe it'll hit the Yucatan again. Who knows? Like that one that killed the dinosaurs, remember? That one? Let's see. You know what? You should try this one yourself. These are getting to be similar enough, I think, that you should try this. Build your confidence. Pause the tape, so to speak. Give this a twirl, and when you're done, come on back and compare what you got to what I got. Okay, so how do these things go again? First of all, we got this thing happening, this arrival happening. What's arriving? Hurricanes. We've got 27 hurricanes arriving every 160 years. So we're going to model the arrival of hurricanes as a Poisson random arrival process. Okay, cool. First thing we need to identify is what's the period we're interested in. We're interested in a 10-year period. We want to look at every 10-year period. So you say, okay, they're telling us it's 27 every 160 years. So the question is, how many are we going to get every 10 years? And that how many are we going to get is what we call the mu. How many are we going to get every 10 years? And when you solve this out, crisscross applesauce, I got like a 1.6875. So more than once, more than 1.5, more than 1.5 hurricanes. Now, when they say probability it gets hit again, okay, see, you got to do a lot of, being careful with the wording. It gets hit again. Are they telling us how many times it gets hit again? No, just it gets hit. So we don't actually care how many times. It's just, did it get hit? So I'm going to say, i.e., at least once. Did it get hit at least once? Well, we can figure out the probability that it does not get hit and take the complement. So the probability it does not get hit at all, e to the minus mu, in other words, e to the minus 1.6875. If you work that out, and I did, you get 0.184981. So the probability that you get hit once or more, x is the number of hits, greater than or equal to 1, would be the complement of that, 1 minus p of 0. And when you do that all out, you get about 815019. Let's call that 81.5%. What do you say? So it's about an 81.5% you'll get hit at least once in the next 10 years. I don't know if I want to build anything real big on that property. Let's see. Okay, that's two kinds. That's the exactly once, or not exactly once. That's the at least once, which is the complement of none. So in other words, we've looked at how many do we expect on average as a 95% interval. Those are the first problems we looked at. We looked at what's the probability of getting completely missed, and of course the complement of that is getting hit once or more. Well, the general case would be, what's the chance we get hit a certain number of times? You might remember the Bernoulli trials. The formula was, for Bernoulli trials, we had this formula for p of x. And you might remember it had some kind of an n choose r and so on in it. But that's what we want here. We want a p of x. I want x to be any particular number of arrivals I'm interested in. And I want to be able to figure out the probability of getting exactly that many arrivals. In fact, let's write that there. Exactly x successes, or in this place, exactly x arrivals. There is a nice formula for it. I just got to give it to you, right? It goes like this. You take that mu thing that we've been playing with, and you raise it to the x power. That's how you get started. Then you multiply that by that e to the minus mu. That's the same e to the minus mu. And on the bottom, you put x factorial. Have you seen the factorial before? So, like 5 factorial means 5 times 4 times 3 times 2 times 1 and so on. Actually, you might be able to see that button on your calculator. I've got a button on my calculator for factorial, so if you could find the button, that'll make it easier. Anyway, so that's the formula we're going to use. Let's switch colors again. Let's look at Biff's beach. Oh, it's the same beach. I get it. 27 hurricanes in the last 160 years. Probably it gets hit exactly twice in 10 years. Well, this was 10 years, right? So the mu is the same, because it's the same period of 10 years that we're interested in. But now we're going to say, what's the probability that it gets hit exactly twice? In other words, x is going to be 2 in this formula. We're going to get hit exactly twice. The probability of getting hit exactly twice is, first of all, you take the mu. We already figured out the mu. It's 1.6875. 1.6875. You raise that to the x power, which is 2. Okay, now you take that e to the mu thing that we've been playing with. So e to the, minus mu, to the negative 1.6875. Oh boy, I got to get used to these pens. I'm still not used to these pens. Negative 1.6875. There we go, and that's supposed to be an e. That goes over, take the x now, and the x is 2 factorial, which basically just means 2 times 1. It's the same as 2. But you can hit the factorial button on your calculator too. And if you work this all out, and you should do this to make sure you can punch the right buttons and all that, you get about 0.263381. Let's agree to call that 26.3%. So there's a 26.3% chance of getting hit by exactly 2 hurricanes in the next 10 years. 81% chance that you'll get hit by at least 1. 26% chance that the number you're getting hit by is exactly 2. Of course, there's a certain chance you're going to get hit by exactly 1, by exactly 3, by exactly 5, by exactly 18,000. You know, all of these can be calculated using that formula. So that's a nifty formula. You want to keep it handy. And actually, I put it on the top of the next page, so that's pretty handy, right? That'll be handy for our last example. So there it is. That's the probability of exactly x arrivals. By the way, notice, what happens if you plug in x equals 0 in this formula? Well, anything to the 0 power is equal to 1. And by the way, 0 factorial, you can ask your calculator, but it's defined as 1. So this is a 1, and this is a 1, and so you're back to e to the minus mu. E to the 0. P of 0 equals e to the minus mu. Yep, that's what we expected. So the formula always works, actually. So that's pretty good. Now, let's use it. What do we got going on here? We got hurricanes again. 530 hurricanes over the past 100 years. That's historical data. Find the probability that at least 4 more show up this year. Okay, always your first task is to figure out what's the period of interest. Period of interest is basically 1 year. So if we had 530 arrive in 100 years, how many do we expect to arrive in 1 year? Set up a nice proportion, solve for the mu. Did I do this one? Please say I did. Yes, I did. Good. It comes out to 5.3. So we're expecting, on average, not every year, but on average, over the long haul, as we repeat the years over and over and over forever, we expect an average of 5.3 hurricanes per year. Assuming there's no changes in whatever. But we expect about 5.3. Okay, cool. Now let's use this formula and go one at a time. So the chance of never getting hit is... Well, that's when the formula simplifies to simply this. So you go e to the minus 5.3, and I worked it all out, and I got a 0.004992, and I'm going to use 6 decimal places. Probably exactly 1 hit. Well, now the formula is a little more complicated. You're going to have to take that mu, which is 5.3, and raise it to the 1 power. X is 1. And then you're going to have to take that, well, same thing, e to the negative 5.3. That part's always the same, actually. Put it over 1 factorial, which is just 1. And make sure you can work this out and get exactly the same thing as me. I got a 0.026455, rounded to 6 decimal places. Cool, right? Let's keep going. Get the pattern going here. Probability of exactly 2 hits. Well, again, look at the formula. You take the mu, which is 5.3. Now we raise it to the 2 power. This part's always the same. And then this is going to be a 2 factorial. So you can see the parts that are changing. What's changing is this exponent and this factorial. Those are the parts that are changing. If you want the probability of 2, that's a 2, that's a 2. And that's really the only parts that change. So what did I get here? I got a 0.070107. Okay, let's do another one. Probability of exactly 3 hits. 5.3 to the, guess what? 3. E to the negative 5.3. That's an E. Over, and guess what? 3 factorial. Okay, so that's the only part of the formula that keeps changing. You keep changing here, it keeps changing that, and the exponent there. Let's get these arrows out of here. They're messing things up. Okay, work that out. Make sure you get exactly the same numbers as me. 0.123856, rounded to 6 decimal places. By the way, question for you. Why are these numbers increasing? 005, 026, 070, 124. They keep increasing. Why is that happening? Do you have a reason? I have a reason. We're expecting 5, right? So I'm just going to say, well, mu is 5.3, so this distribution, that's what you call it when you say all these numbers put together. It makes a distribution. So this distribution should peak around 5. So what you should find is that the next 2 numbers will probably be even bigger than 0.12, and then it'll start to get small. And when you get to like 10 and 11, it's going to be so small, it's going to be unbelievable, and you're going to get tired of calculating it. Fortunately, I don't think we have to keep calculating it. Why not? What have we got so far? We've got the chances of 0, 1, 2, and 3. What are we interested in? 4 or more. Maybe you're starting to see this. So the chance of getting 3 or less, x less than or equal to 3, you could take the probability of 0 and add the probability of 1 and add the probability of 2 and add the probability of 3. In other words, the numbers that we just calculated. And if you add those all up, you get, where is it? Where is it? There it is, 0.225410. Okay. Why can I simply add? Because these are mutually exclusive. You're not going to have exactly 0 and at the same time exactly 1 and at the same time exactly 2, right? These are all, you can't have, they're mutually exclusive. So you can just add them up simply. So the probability of having 4 or more is going to be 1 minus the probability of 3 or less, because those are called complements. They exhaust all the possibilities. You either have less than or equal to 3 or you don't. And if you don't, it's because you have greater than or equal to 4. So they're complements, and so you go 1 minus that, and you end up with like a point, come on pen, equals like a 0.77459. And this is the part where you say, okay, let's make an artistic choice about where to round. I'm going to call it like 77.5%. I think that number would make a lot of sense. Hey, chance of getting hit by 4 or more hurricanes in the next year. The period of interest was just 1 year. 77.5%. So it's a pretty good chance there's going to be at least 4 hurricanes this year. Okay, so Poisson arrival process. It's pretty cool. It's very similar to binomial distribution, really. And really the main difference between the two in terms of calculating things is this, well, I guess you would have to say this was a difference, right? That formula is different than the binomial distribution formula. But I was going to say the other thing is that for the binomial you had sigma equals square root of NPQ, whereas for this one you have the very simple sigma equals square root of mu. So kind of fun. But I love thinking in terms of the bus never coming, or when's the next hurricane or tornado going to get here, or when's the next whatever. There'll be more examples on the homework. Hope you enjoy as much as I do.